Out there in the critical obscurity of space, the James Webb Space Telescope has been researching the dark for replies about the universe. It's NASA's new eye above and has been discovering stunning pictures of stars, huge systems, and planets. At any rate, before long, something surprising has been tracked down. Something so enormous it could shake the very spines of all that we know. It has researchers scratching their heads and analyzing whether it could prompt the farthest limitation of everything. Join us as we investigate how the latest discovery of the James Webb Space Telescope could destroy the universe. At the point when we investigate the edge of the universe, it is the noticeable early phase. The noticeable universe looks like a window through which we can research the tremendousness beyond the discernible universe. It envelopes everything that we can at present recognize, measure, and explore using our telescopes and space tests. It's an assortment of stars, universes, and heavenly bodies within our degree of understanding. At any rate, the discernible universe is just a little piece of the whole universe. Imagine it as a bit cut of an enormous, unfathomable pie that we're able to study and fathom, while the total size and condition of the universe at large remain a mystery. Researchers estimate the width of our conspicuous bubble to be around 93 billion light-years. A light-year measures the distance that light, the fastest thing in the universe, goes in 1 year, around 588 trillion meters or 946 trillion kilometers. So, when we examine the expansiveness of the detectable universe being 93 billion light-years, we're examining a huge stretch. Around 13.8 billion years ago, the universe burst into existence in an unfathomably strong impact. This impact began what we call the Big Bang. Since that momentous birth, the universe hasn't simply been growing. It's been advancing rapidly in its extension. Baffling forces like the mysterious dark energy give off an impression of being driving the speed increment, pushing the limits of the universe farther and farther apart. As the universe extended, matter began to mix under the impact of gravity. This gravitational force joined particles, birthing dazzling plans, stars, astronomical systems, and ultimately planets like our own dear Earth. Picture the universe passing by as these huge plans framed, progressing into the different and still maturing quarks we see scattered across the universe today. Regardless of its immense size, the universe is inconceivably empty. Assuming that we were to contract our entire nearby planetary group to the size of a quarter, the closest star would still be about the length of 2 soccer fields away. This tremendousness grows just within our own Milky Way system, which is only one among billions in the observable universe, giving us a sense of the sheer size of limitless space. Now you might inquire as to why we can't just see all that exists in the universe. There are a couple of explanations behind this limitation. Most critically, light, the fastest thing known to humankind, still takes time to travel through space. This means that when we look at distant objects, we're essentially examining the past. The farther an object is, the more its light has traveled to reach us. It's like looking through an unfathomable time machine, unrolling the history of our universe. As we observe systems millions or even billions of light years away, the real universe is growing. Imagine dots on the surface of a blowing up balloon. As the balloon inflates, the dots move farther apart. This same rule applies to the universe. Galaxies, like those dots, are floating apart as the fabric of space expands. This expansion causes the light emitted from distant objects to undergo a shift known as redshift. Essentially, the frequencies of light stretch as the objects move away, shifting toward longer frequencies, often seen as a bronze tone. Given these factors, light's travel time, the expansion of space, and the universe's continuous advancement, it's not surprising that we haven't yet fully observed the entirety of the universe. Even with our highly advanced telescopes and technology, our view remains limited by these key properties of the universe. The journey to understand the possible edge or limits of the universe has enraptured the minds of countless individuals across disciplines. While convincing answers remain elusive, 3 recognizable hypotheses have emerged, each presenting interesting perspectives on the vastness of cosmic space. The first hypothesis suggests that the universe grows unfathomably, continuing on endlessly without a noticeable edge. This idea aligns with the cosmological principle, affirming the isotropy of the universe. is consistent in appearance from any vantage point. If this principle holds, it suggests that the universe has no boundary, expanding perpetually in all directions. The second hypothesis offers an alternative view, suggesting that while the universe may indeed be limited, it lacks a clear edge. Instead, it's like an epic circle or a curved space connected to itself, similar to Earth. In this scenario, if one were to travel endlessly in any direction, they would eventually return to their starting point, like circumnavigating the Earth. The third theory, the multiverse hypothesis, presents a fascinating idea that our universe is simply one among countless others. Imagine endless parallel universes, each existing with its own set of physical laws, constants, and properties. These universes may be completely isolated from one another, operating independently, or they may be interconnected through complex systems, forming a vast and intricate multiverse. The James Webb Space Telescope, JWST, stands as a beacon of potential, illuminating the secrets that shroud the gigantic origins of the universe. This incredible instrument has an unmatched ability to disentangle the confusing past of our universe, allowing us to peer far beyond what was previously possible. The JWST is a mechanical marvel, designed specifically to observe the universe with unprecedented accuracy. Its advanced capabilities extend our vision to the earliest moments of the universe. Recently, a groundbreaking study published in the prestigious journal Nature revealed the JWST discovery of 6 massive galaxies dating back between 500 million and 700 million years after the Big Bang. Incredibly, these ancient galaxies are far larger than expected for their early existence, challenging prevailing ideas about the universe's development and growth in its infancy. What's truly surprising about these discoveries is the level of development of these ancient systems, defying conventional models. These celestial giants display a degree of complexity comparable to our 13-billion-year-old Milky Way. The sheer number of stars inside these massive behemoths surpasses comprehension, each boasting a total mass several times greater than our Sun. Strikingly, one of these galaxies may even have a mass up to 100 billion times that of our Sun, eclipsing the already gigantic size of our Milky Way. The JWST's unparalleled ability to see the universe's hidden regions relies on its use of infrared light, an invisible spectrum to the naked eye. This remarkable power allows the telescope to capture the faint emissions from ancient stars and galaxies, revealing enormous remnants that have endured for billions of years. Essentially, the JWST acts as a time machine, taking us back through the ages and offering a rare look into the universe as it appeared roughly 1.5 billion years ago. The ongoing discovery of massive galaxies, affectionately nicknamed universe breakers, has overturned our understanding. It's akin to rewriting history, a shocking twist that challenges many of the models we had laid out for early galaxies. Initially, we thought galaxies formed from humble beginnings, starting as small collections of stars and dust. They were believed to gradually grow, increasing in size and complexity over time. However, the universe breakers have shattered these assumptions. When the JWST data and its high-resolution images unveiled these titanic structures, they appeared seemingly out of nowhere, upending our previous understanding of cosmic evolution. Digging deeper, scientists used spectroscopic techniques to analyze light across different frequencies. This examination holds the key to unlocking crucial insights about these mysterious galaxies. Details such as their structure, size, and distance from Earth. It's like a vast detective story with light as the clue to uncovering the secrets of these enormous entities. The stunning revelations from the James Webb Space Telescope have propelled our understanding of the universe to extraordinary levels. This cutting-edge telescope, built by a global team of space scientists, has recently uncovered an amazing discovery: the identification of the oldest and most distant galaxies ever observed. These galaxies transport us back to when the universe was just a tiny fraction of its current age, existing only a short time after the Big Bang. The James Webb Space Telescope, out in the immense void of space, has been seeking answers about the universe. It's NASA's latest monumental instrument, capturing stunning images of stars, galaxies, and planets. Recently, it made a discovery so remarkable that it could change how we comprehend the very fabric of the universe, leaving researchers baffled and curious about its potential repercussions. When we examine the universe, we begin with the observable universe, a window into the immeasurability beyond. This observable universe encompasses everything we can currently connect with our telescopes and space probes, including stars, galaxies, and other celestial bodies. However, it's just a small part of the entire universe. Researchers estimate the width of our observable universe to be around 93 billion light-years. A light-year measures the distance light travels in 1 year, roughly 588 trillion miles, making the scale nearly boundless. About 13.8 billion years ago, the universe began with the Big Bang, an epic explosion that triggered the immense expansion. Since then, the universe has been growing and accelerating, driven by mysterious forces like dark energy. Matter began to coalesce under gravity, forming stars, galaxies, and eventually planets like Earth. This continuous development shapes the universe's colossal size, allowing us to observe only a small part of its vastness. Despite its massive size, the universe is surprisingly empty. For example, if our entire solar system were the size of a quarter, the nearest star would still be about 2 soccer fields away. This immensity stretches just within our own Milky Way galaxy, which is just one of billions in the observable universe. We can't see everything due to 2 primary factors: the time it takes for light to cross space and the universe's ongoing expansion. As galaxies move away from us, their light shifts to longer frequencies, making some objects too distant to detect. Scientists use units like light-years to measure these vast distances. Our Milky Way is about 100,000 light-years wide, and the closest star to the Sun, Proxima Centauri, is 4.24 light-years away. Observing galaxies billions of light-years away lets us explore the past, seeing them as they were billions of years ago. This vast expansion also means our observational limits are constantly being pushed as the universe accelerates. 3 primary theories try to explain the scale of the universe. It could endlessly grow, it could be limited but without a clear edge like a giant circle, or our universe could be one of many in a multiverse, each with its own physical laws. These theories, while speculative, spark scientific curiosity and philosophical reflection, testing how we understand space's limits and existence. The James Webb Space Telescope has provided crucial insights into early universe development. Designed to observe the universe with unparalleled precision, it has recently discovered 6 massive galaxies dating back between 500 and 700 million years after the Big Bang. These massive galaxies surprisingly appear much older than expected, challenging current theories about cosmic development. The JWST's ability to see the universe's mysterious regions depends on its infrared capabilities, allowing it to observe ancient stars and galaxies that have existed for billions of years. The discovery of these universe breakers suggests that early galaxies were far larger and more developed than previously thought, leading to a deeper understanding of the universe's history. The discovery of these universe breakers by the James Webb Space Telescope has set the scientific community abuzz with new questions about the early universe. The data, which seems to defy established models of galaxy formation, is compelling scientists to rethink how galaxies evolve. These massive galaxies, with their high star counts and dense structures, suggest that the universe may have had a much more rapid and complex early evolution than previously imagined. Such findings open up new avenues for understanding cosmic growth, especially considering that galaxies of similar size were not thought to exist so soon after the Big Bang. One of the most intriguing aspects of this discovery is that these galaxies appear to be already well-formed despite the relatively short time since the Big Bang. This could imply that certain cosmic processes that were previously believed to take much longer may have occurred much faster than anticipated. Scientists are now trying to figure out how these galaxies could have developed such complexity in such a short span of cosmic history. Could the early universe have been governed by different rules, or did certain conditions, such as the density of dark matter or the rate of star formation, accelerate the process? Furthermore, these findings challenge the prevailing models of galaxy formation that suggest galaxies should begin small and gradually grow over billions of years. If these galaxies existed so soon after the Big Bang, it could indicate that the processes of galaxy assembly were much more efficient in the early universe than scientists had assumed. The rapid formation of these giant structures might also provide clues about the mysterious forces that shaped the early universe, such as the role of dark energy in accelerating the expansion of space. Beyond the implications for galaxy formation, the discovery of these ancient, massive galaxies could also influence our understanding of star formation and black hole growth. Massive galaxies typically harbor supermassive black holes at their centers, and these early galaxies might have already hosted such behemoths, which raises new questions about how quickly supermassive black holes could have formed. These black holes might have played a crucial role in shaping the surrounding galaxy, controlling star formation through feedback mechanisms, and impacting the growth of structures in the universe. The ability to observe these ancient galaxies and their features in such high detail marks a significant milestone in astronomical research. The James Webb Space Telescope's infrared capabilities allow it to see through the cosmic dust and gas that typically obscure our view of distant objects, offering scientists unprecedented insights into the conditions of the early universe. This level of clarity was previously unattainable, even with other powerful telescopes like Hubble. The JWST's observations are offering a glimpse into a time when the universe was still young and its structures were just beginning to take shape, providing invaluable data that will inform research for years to come. As more discoveries are made using JWST, scientists are poised to unlock even more secrets about the origins of the universe, potentially altering our very understanding of cosmic evolution. The telescope's ability to peer deeper into the universe's past promises to reshape many of the current models of the universe, leading to a new era of space exploration where the most distant and ancient corners of the cosmos become visible.